Hi students, the topic of this video is conservation of energy. Energy can be defined as the capacity for doing work. We know that the work done is the change in energy. It may exist in a variety of forms: kinetic, potential, heat energy, chemical energy, and may be transformed from one type into another. However, these energy transformations are constrained by a fundamental principle, the conservation of energy principle. That means that energy can neither be created nor destroyed. That means that the total energy of an isolated system remains the same. So by conservation of energy, the energy before, the total energy before should be equal to the total energy after. For example, when we drop an object from a height of h, here it is stationary, that means that no velocity, so no kinetic energy. It has just potential energy. So the total mechanical energy is equal to mgh. When it strikes the ground, it has zero potential energy because no height, and it strikes the ground with a velocity of v, so has a kinetic energy 1 over 2 mv square. So here the total energy is equal to 1 over 2 mv square. From the conservation of energy, the total energy, mechanical energy at the initial should be equal to the total mechanical energy at the final. So mgh should be equal to 1 over 2 mv square, because the energy initial should be equal to the energy final. It's characterized from location A to location B equals the friction-free ice as in the figure. Now we see that at A we have a height of h1, and at B it has a lower height h2. So from the mechanical energy conservation, the total mechanical energy at A should be equal to the total mechanical energy at B. Let's say it has no velocity at point A, so no kinetic energy, just have potential energy equal to mgh1. So the total mechanical energy at A is equal to mgh1. At B, it has a potential energy, mgh2. As h2 is smaller than h1, then the total potential energy at B is smaller than the total mechanical energy at A, so it should have a kinetic energy here. So the square should have a velocity of v here, is equal to 1 over 2 mv square. So the total mechanical energy at B is equal to mgh2 plus 1 over 2 mv square. So from this equation we can find the unknown. The spring of a dart gun exerts a force on a dart as it is launched from an initial rest position. When I squeeze it, I deposited a potential energy to the dart, which is equal to 1 over 2 kx square. So when it is launched, this potential energy is transferred into the dart, so it will have a kinetic energy which is equal to 1 over 2 mv square. So from the conservation of energy, the potential energy deposited in the gun should be equal to the kinetic energy transferred to the dart. In a bungee jumping, the bungee cord begins to exert an upward force upon a falling bungee jumper. When you go down, the cord will apply a force because it will be squeezed with an amount of, let's say, x. So the change in the potential energy of the boy will be transferred into the elastic potential energy of the cord. So the change in potential energy is transferred into the elastic potential energy on the court. Here we see a pendulum, and we're going to find the height and the velocity of the object at positions 1, 2, 3, and 4. We are going to assume this the base of the motion as the height is equal to 0. At the position 1, the potential energy is 6. As potential energy is equal to mgh, let's put the value. 6 is equal to mass 1 times g10 times height. So the height is equal to 0.6 meter. Here it is released, so you see that it has no velocity, so no kinetic energy. At the position 2, the potential energy is 3, so 3 is equal to m times g times h, so the height is equal to 0.3 meter. So you see that 3 joules of kinetic energy is gained from the transformation of the lost in potential energy. So kinetic energy is equal to 1 over 2 mv square. So 3 is equal to 1 over 2 times 1 times v square. So I have the velocity root square 6 meter per second. At point C, you are at the base, so height is 0, so the potential is 0. So D is equal to 0. Let's write here. Now I have the kinetic energy 6. You see that the all potential energy at the position 1 is converted into kinetic energy here. So 6 is equal to 1 over 2 times mass times v square. So the velocity is equal to square root 12 meter per second. At position 4, the kinetic is 0, so velocity is 0. The potential is 6. So you see that the position 4 is the same as the position 1. So the height should also be the same, which is equal to 0.6 meters. We know that non-conservative forces changes the mechanical energy. So a force that increase or decrease the total mechanical energy, like the force provided by a motor or engine that increase in mechanical energy, or friction that decrease in mechanical energy, are all non-conservative forces. So we are usually going to use the friction force. The friction force, the work done by the friction force, is a change in energy, but this will be a decrease in mechanical energy. Consider an object on a slide sliding down a 10-meter long hill on a 30-degree incline. The mass of the object is 2 kilograms and it has a velocity of 2 meters per second when at the top. If the velocity of it is 10 meters per second at the bottom of the hill, how much work is done by friction? Now, work is done by friction is the change in energy. That means that the final energy minus the initial. So I'm going to find these energies. So as the angle is 30 degrees, then the height should be the half of the hypotenuse, which is equal to 5 meters. Let's say this is the position A and this is the position B. At the position A, it has a potential energy which is equal to from mgh 2 times 10 times 5, which is equal to 100 joule. It is also a kinetic energy which is equal to 1 over 2 mv square, 1 over 2 times 2 times 2 square, which is equal to 4 joule. So the total mechanical energy at A is equal to 104 joule. At the position B, it has no potential energy because you see that the height is equal to 0. It has just the kinetic energy, which is equal to 1 over 2 mv square, 1 over 2 times 10 square, so 100 joule. So the total mechanical energy at B is equal to 100 joule. Now I see that the mechanical energy at A is 104 and the mechanical energy at B is 100 joule. So it is not conserved because friction is a non-conservative force, so it changes its mechanical energy. So the change in mechanical energy is equal to 104 minus 100, which is 4 joule, and this is the work done by friction. A 2 kilogram object going with a constant velocity of 10 meters per second enters a region with a friction at point K. Here it enters the region with a velocity of 10 meters per second. How many meters from the point K will the object stop? Let's say that it will stop here, so has a zero velocity, and this distance is asked. Now the coefficient constant is given, so I can find the friction force from K times normal. K is equal to 0.2. The normal is the weight of the object 20, so the friction is equal to 4 Newton. Now we know that the work done by friction is equal to the change in kinetic energy. So this is the initial position, this is the final position. The energy initially is equal to 1 over 2 times mass times the velocity square 100 joule. And the final energy is equal to, as the velocity is 0, 0. So the change in energy is equal to minus 100 joule. That means that the work done by friction is minus 100 joule, which is equal to minus F times the distance. I know the F, so minus 100 is equal to minus 4 times X. So I have the X equal to 25 meters. Find the velocity of the 4 kilogram object going initially with a velocity of 6 meters per second. It has an initial velocity 6 meters per second, and its velocity at the point L is asked. The coefficient constant of friction is given as 0.4. So first let's find the friction from the formula K times M. 0.4 times the weight of the object, it is equal to 40 Newton. The work done by friction is equal to change in energy, so the final energy at L minus the initial energy at K. The work done by friction is negative, so minus 16 times the distance 0.5 is equal to 1 over 2 times mass times v square minus 1 over 2 times mass times the initial velocity square. So minus 8 is equal to 2v square minus 72. 2v square is equal to 464. V square is equal to 32, so V is equal to 4 square root 2 meter per second. In this example, we have a 2 kilogram object which changes its velocity from 4 to 6 meters per second in 5 seconds, and we are going to complete the work kinetic energy bar chart for this process. Now let's find the initial energy from 1 over 2 mv square. Mass is 2, velocity is 4 square, which is equal to 16 joule. The final energy is equal to 1 over 2 times 2 times the 6 square. It is 36 joule. So you see that the change in energy is equal to 20 joule, which is equal to work done. So in order to complete the charge, I'm going to convert them to basic constants. If I say this is for E, then this is equal to 9E, and this is equal to 5e. So I have initially 4e. Let's say that this is the 0 point. So 1, 2, 3, 4. I have this amount of energy, and 5e amount of work is done on the object. 1, 2, 3, 4, 5. So the final energy of the system becomes 9e. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I complete the chart by using the ratios. Efficiency, the ratio of energy which was transferred to a useful form compared to the total energy initially supplied, is called the efficiency of the device. That means that efficiency is the ratio of energy used over the energy supplied. It can be written as decimals like 0.33 or percentages like 33%. To convert the efficiency expressed as a decimal to a percentage, you just need to multiply by 100. So this is the formula of the efficiency. Let's do an example. What's the efficiency of a leg muscle if it converts 450 joules of chemical energy into 90 joules of movement energy? This is the energy supplied, and this is the energy used. So efficiency is equal to energy used over energy supplied by 100. So this is equal to 20%. So 20% of the chemical energy is converted into just movement energy. Energy cannot be created or destroyed. We have talked about it in energy conservation. It can only be transferred from one form into another. Energy that is wasted, like the heat energy from an electric lamp, doesn't disappear because heat is also an energy form. Instead, it's transferred into the surroundings and spread out so much that it becomes very difficult to do anything useful with it. Now here we have two lamps, a filament lamp and an energy efficient lamp. You see that in a filament lamp you use 100 joules of energy, and just 10 joules of energy is converted into light energy, and approximately 90 joules of energy is converted into heat energy. But in an energy efficient lamp, the 100 joules of energy is converted 75 joules of light energy, just 25 joules of heat energy. So we think of the heat energy as waste energy because we are not using a lamp to get heat. We use it to get light. So you see that it has more conversion of light compared to the filament lamp. So I recommend you to use the energy efficient lamps. That's why. Now let's do the classwork. The first question: compare the velocities of the given objects when they reach the ground. At this position they have potential energies, and they reach the ground, it is converted into kinetic energy. So mgh is equal to 1 over 2 mv square. You see that the masses cancel each other, so v square is equal to 2gh. So velocity just depends on the height. So the object in position 3 has a bigger height 2h, so it will have more velocity. These have the same heights, so we'll have the same velocities. Acceleration time graph of a 2 kilogram object is as in the figure. The initial velocity of the object is 5, so what is the final kinetic energy of the object at t is equal to 8 seconds? We know that the area under the acceleration time graph will give us the change in velocity. So here the area is equal to 4 meters per second, and between 2 and 8 seconds the area is equal to minus 6 meters per second. So in total the change in velocity of the object is minus 2 meters per second. So the final velocity is equal to the initial velocity plus the change in velocity. The initial velocity is 5 plus the change is minus 2. So the final velocity of the object is 3 meters per second. So the final kinetic energy from the formula 1 over 2 mv square, 1 over 2 mass 2 kilogram times the velocity 3 square, which is equal to 9 joules of energy. Question 3. When a given system which can rotate freely around O is released, what will be the change in potential energy when it becomes vertical? 2 Newton has more weight than 1, so the system will turn in clockwise direction. 2 Newton come here and 1 Newton will come here. This is the initial position and this is the final position. So let's say that this level is the level that the height is equal to 0. So let's find the total potential energy initially. 2 Newton has a height of 1 meter, so initially it will have a potential energy 2 times 1 plus 1 Newton has a height of 1 meter, 1 times 1, so in total 3 joules of energy. When they become vertical, you see that 2 Newton is at a height of 0, so it has no potential energy, and 1 meter has a height of 1 Newton has a height of 2 meters, so the final energy is equal to 1 times 2, which is equal to 2 joules. So you see that the change in energy is equal to final minus initial minus 1 joule. Question 4. The given 2 kilogram object thrown with an initial velocity of 6 meters per second from the point K. Stop at the point L. Find the friction force between the object. We know that the work done by friction is the change in energy. So the energy at K is equal to 1 over 2 times mass times the velocity square 26 joule. And the final energy at point L is 0 because it has 0 velocity. So the change in energy is equal to minus 36 joule. So the work done by friction, which is equal to minus F times distance, is equal to minus 36 joule. F times the distance is 2 meters is equal to 36. So the friction force is equal to 18 Newton. Question 5. The kinetic energy of an object decreases from 60 joule to 20 joule after it takes a distance of 8 meters. Find the force of friction of the surface. We know that the work done by friction is equal to change in energy. So the final energy minus the initial energy. You see here that the final energy is 20 minus initial is 60. So minus 40 joules of work is done by friction. The work done by friction is equal to minus F times distance is equal to minus 40. The distance is equal to 8, so F times 8 is equal to 40. So force of friction is equal to 5 Newton. The last question, if a 3 kilogram object rises up 10 meters with a 35 Newton force applied, first we are going to find the work done by the force F. It goes up with a distance of 10 meters. So the distance and the force, they are in the same direction. So the work done by F is equal to F times the distance. So 35 times 10, which is equal to 350 joules. Find the work done by gravity. The weight of the object is 30 Newton. So you see that the direction of the weight and the distance taken are opposite in direction. So the work done by gravity is negative. Minus 30 times 100 is equal to minus 300 joule. The net work done is equal to the sum of the work done, 350 plus minus 300, which is equal to 50 joule. The kinetic energy it gains, the net work done is equal to the change in kinetic energy, so it is equal to 50 joule. The potential energy it gains, the potential energy is equal to mg times h. Mass is equal to 3, g is equal to 10, the height 10, so it gains 300 joules of potential energy.